The night sky is a beautiful lie. Those glittering stars are separated by a profound darkness so deep and vast it feels like nothing. But that darkness is not empty. It is a hidden ocean, a churning, invisible sea that holds the galaxy together. We call this the interstellar medium. It is the space between the stars, and it is filled with more mysteries than the stars themselves. By the end of this journey, you will see the galaxy not as a collection of lonely lights, but as a single, breathing organism with secrets in its veins. This cosmic ocean is a soup of ghostly gases, strange dust, and forces we are only beginning to comprehend. We will dive into 25 of its deepest puzzles, from the origin of complex molecules that smell of rum to the search for half the universe's missing atoms. What do you think is the most surprising thing hiding in the darkness between the stars? Our first mystery is hiding in plain sight, yet it blankets the entire galaxy in darkness. This is the mystery of cosmic dust. Think of it as the soot of the universe, but this is not simple household dust. These are microscopic grains, smaller than a wavelength of light, forged in the violent deaths of stars. When a massive star explodes as a supernova, or when an aging red giant star gently puffs its outer layers into space, they spew out newly created elements. Carbon, silicon, iron, and oxygen are flung into the void. In the cooling aftermath, these atoms clump together, forming solid particles of graphite, silicates, and even ices. This stardust is the raw material for everything rocky, from asteroids to Earth itself. But here is where the puzzle begins. The math does not add up. When astronomers calculate how much dust should be produced by all the dying stars we observe, the numbers fall short. There seems to be more dust out there than our stellar factories should have supplied. Where is the extra coming from? Perhaps there are dust producers we have not yet fully accounted for, like colliding neutron stars or peculiar types of stellar winds. Even more perplexing is the dust survival. Space is a brutal environment. Shockwaves from later supernova blast through clouds, radiation from hot stars batters the tiny grains, and violent collisions should shatter them to atoms. Yet the dust persists. It must be constantly replenished, or it must be far more resilient than we think. These fragile grains are not just cosmic clutter. They are essential. They shield forming stars, help gas clouds cool and collapse, and their surfaces are where the first complex molecules, the precursors to life, can safely assemble. The origin of cosmic dust is not a trivial question. It is the mystery of our own origins, written in microscopic specks that dim the light of distant suns. How did something so delicate become the foundation for worlds? These cosmic dust grains are the seeds of worlds, but they float within something far more elusive. If we could weigh the entire universe according to the Big Bang's recipe, we would find a shocking discrepancy. Roughly half of all the normal matter, the atoms that make up everything you see and touch, is simply missing. This is the great missing baryon problem, and it is one of cosmology's most embarrassing puzzles. We are not talking about dark matter, that mysterious substance that outweighs normal matter 5 to 1. This is about the ordinary stuff, the protons and neutrons called baryons that should be here. The math from the afterglow of the Big Bang tells us precisely how much of this ordinary matter was created. Yet when we add up everything we can see, all the stars, galaxies, gas clouds, and planets, we come up short by a staggering 50%. So where did half the atoms in the universe go? The prime suspect is the interstellar medium, but in its most extreme and ghostly form. Astronomers believe the missing baryons are not in bright galaxies, but are instead spread throughout the vast cosmic web, the filamentary structure of the universe. They are hiding in what is called the warm-hot intergalactic medium, or WIM. Picture this as a superheated, incredibly thin fog filling the spaces between galaxy clusters. This gas is so hot, millions of degrees, that it glows not in visible light but in faint X-rays. It is also so diffuse that a volume of it the size of your average bedroom might contain only a single atom. Trying to detect it is like trying to see a whisper in a hurricane. Our telescopes struggle to pick up its faint signal against the brilliant backdrop of the universe. Finding this missing matter is not just about balancing a cosmic ledger. It is crucial for understanding the complete story of how galaxies form and evolve. This hot gas is the reservoir from which galaxies drew their material, and it is the medium through which they interact. Mapping the WIM is like finally seeing the waterways that connect all the islands in an archipelago. We have the maps of the islands, the galaxies, but without the water, we cannot understand how life, or in this case starlight, travels between them. Until we can account for every last atom, our picture of the universe remains fundamentally incomplete, a beautiful tapestry with half its threads still invisible. That missing matter is hidden in a ghostly fog, but some interstellar secrets leave a clearer signature. Starlight itself holds a chemical fingerprint of the space it travels through. For over a century, astronomers have been staring at a set of mysterious dark lines etched into that light, a cosmic barcode no one can fully decipher. These are the diffuse interstellar bands. When light from a distant star passes through a cloud of interstellar gas and dust, specific colors are absorbed. This creates dark lines in the star's spectrum, each one a telltale mark of a particular atom or molecule, like a unique signature. We know the signatures of hydrogen, helium, and simple molecules. But scattered among these familiar lines are hundreds of others that do not match anything we have ever seen in a lab on Earth. They are the unidentified flying objects of astronomy, persistent, mysterious, and utterly pervasive across the galaxy. We know they come from complex molecules drifting in the interstellar medium. Their very existence tells us the space between stars is not just a simple soup of atoms, but a rich chemical brew. But the exact identity of the molecules creating these bands has remained one of the field's most stubborn puzzles for over 100 years. The leading suspects are large carbon-based molecules. Imagine structures like polycyclic aromatic hydrocarbons, which are essentially tiny, flat flakes of soot or even fullerenes, the famous soccer ball-shaped cages of carbon atoms nicknamed buckyballs. These are sturdy, complex molecules that could survive the harsh interstellar environment. The problem is proving it. Laboratory scientists try to recreate space conditions and measure the light absorbed by candidate molecules, searching for a perfect match to one of the hundreds of mysterious lines. It is a painstaking game of cosmic fingerprint matching. Solving this century-old riddle is not just an academic exercise. These unidentified molecules are likely a major reservoir of cosmic carbon. They are the building blocks for more complex organic chemistry, the kind that could eventually lead to the precursors of life on new worlds. By identifying the carriers of the diffuse interstellar bands, we would unlock a hidden chapter in the chemical evolution of our galaxy. We would know what raw materials are truly floating out there in the dark, waiting to become part of something new. What if these unknown lines are the signatures of compounds we have not even dreamed of yet? Those mysterious chemical fingerprints drift in a sea of invisible bullets. This brings us to our fourth mystery, the source of the galactic cosmic rays. Our entire solar system is constantly being bombarded by these high-energy particles, mostly protons, moving at a staggering 99.99% the speed of light. They are nature's ultimate particle accelerators, and they are coming from somewhere out there in the galaxy. For over a century, we have been trying to find the gun. The prime suspect has long been the shock waves from supernova remnants. When a star explodes, it blasts a shell of debris outward at millions of miles per hour. This creates a titanic shock front, a propagating wall of energy that can trap charged particles and whip them around, accelerating them to phenomenal speeds over thousands of years. It is a compelling and beautiful theory, a celestial engine recycling stellar death into high-energy radiation. yet the evidence is not a perfect fit. When we analyze the cosmic rays that actually reach Earth, their energy spectrum and their chemical composition do not align perfectly with what our models of supernova accelerators predict. There is either something we do not understand about how supernova work, or we are missing a major contributor to the cosmic ray population. So what else could be powering these particles? The suspects are numerous and exotic. Rapidly spinning neutron stars or pulsars generate intense magnetic fields that could act like colossal slingshots. The relativistic jets screaming from the vicinities of supermassive black holes in active galaxies are capable of unimaginable particle acceleration. Some theorists even speculate about more dramatic events, like the mergers of neutron stars or the annihilation of dark matter particles. The truth is, our galaxy is likely filled with multiple types of cosmic ray factories, each contributing to the torrent that washes over us. Solving this mystery is not just about cataloging celestial violence. These cosmic rays are a fundamental part of our space environment. They penetrate the heliosphere, the protective magnetic bubble blown by our sun, and shower down on planetary atmospheres. They can influence cloud formation on Earth and may have played a role in the evolution of life by causing genetic mutations. They are also a major hazard for astronauts and satellite electronics. To truly understand our place in the galaxy, we need to know what is shooting at us and why. The search for the source is a hunt for the most powerful engines in the Milky Way, hidden somewhere in the dark. These high-energy bullets do not travel through empty space. They navigate an invisible maze, a ghostly force field woven through the very fabric of the galaxy. This is the mystery of interstellar magnetic fields. You cannot see them, you cannot touch them, but their influence is everywhere. They are the silent architects of the cosmic ocean. Picture the galaxy threaded with lines of magnetic force, tangled and twisted like a web spun by a spider in a hurricane. These fields are astonishingly weak, millions of times weaker than a common refrigerator magnet. Yet across light years, their collective power is immense. They shape the birthplaces of stars, they guide the deadly cosmic rays we just discussed, and they hold entire clouds of gas together against the forces that would tear them apart. But how do you map something you can never directly see? Astronomers become detectives of subtle effects. One clue comes from starlight itself. As light travels through clouds filled with these needle-like dust grains, the magnetic fields gently align the grains, all pointing in the same direction like iron filings near a magnet. This aligned dust polarizes the starlight passing through it, twisting it in a specific way our telescopes can detect. It is like seeing the faint shadow of the invisible web cast upon the light of distant suns. Another clue comes from a phenomenon called synchrotron radiation. When those ultra-fast cosmic rays, electrons mostly, spiral along the magnetic field lines, they emit a faint radio glow. By mapping this radio whisper across the sky, we can trace the outlines of the magnetic fields that confine them. The maps we are building reveal a structure of stunning complexity and surprising order. Fields stretch along the spiral arms of the Milky Way, but they are also crumpled and folded at smaller scales by turbulent gas motions. This leads to the core of the mystery. How did these fields get so strong, and how do they maintain their coherence over such incredible distances? The leading theory is a cosmic dynamo. Just as the moving molten iron in Earth's core generates our planet's magnetic field, the turbulent, churning motions of ionized gas in the interstellar medium could amplify weak seed fields. These seeds might be primordial, left over from the universe's infancy. Over billions of years, the gas motions stretch, twist, and fold these magnetic lines, transferring the energy of the turbulence into the magnetic field, making it stronger. But the details are maddeningly complex. The math of magnetohydrodynamics, the interplay between magnetic fields and conducting fluids, is some of the most difficult in all of physics. We do not fully understand how the field reaches an equilibrium, why it does not simply tear itself apart, or how it manages to influence the collapse of a gas cloud into a star without stopping it completely. These fields are a cosmic balancing act. They provide the skeletal support that allows a cloud to condense, but they also exert a pressure that can resist gravity's pull. The outcome of this tug-of-war determines the size, the shape, and even the number of stars a cloud will give birth to. To understand the story of star formation, we must first learn the language of this invisible, tangled web. It is the silent script written across the darkness, directing the most important drama in the cosmos. That invisible magnetic web gathers the raw materials for creation in places of profound darkness. Deep within the spiral arms of our galaxy lie vast, cold clouds so dense they blot out the light of the stars behind them. These are the dark molecular clouds, the stellar nurseries of the cosmos. From the outside, they appear as silent, black voids, cosmic ink blots against the Milky Way. But step inside their frigid hearts and you find a mystery of astonishing activity. In temperatures just a few degrees above absolute zero, in near total darkness and under pressures far thinner than any vacuum we can create on Earth, a rich and complex chemistry is brewing. This is the hidden chemical factory of the galaxy. The primary ingredient is simple molecular hydrogen, two hydrogen atoms bonded together. But floating alongside it are traces of other atoms, carbon, oxygen, nitrogen, sprinkled throughout like spices in a vast, dark soup. Alone, these atoms would rarely meet and react in the sparse void. They need a meeting place, a solid surface. That is where the cosmic dust grains become essential. Think of each microscopic speck of interstellar dust as a tiny, frozen laboratory bench drifting in the dark. When a lone hydrogen atom or an oxygen atom bumps into one of these dust grains, it sticks, held by weak forces in the extreme cold. It waits, soon another atom drifts in and sticks right next to it. Now, on the surface of this grain of stardust, two atoms that would have sailed past each other in open space are forced into an intimate dance. With a tiny nudge from the faint background heat or a cosmic ray zap, they link together. Step by painstaking step on these minuscule platforms, molecules are built. Water ice forms, carbon monoxide links up, methanol, a simple alcohol, assembles itself. Astronomers have even detected the fingerprints of glycolaldehyde, a simple sugar, in these clouds. This is probiotic chemistry, the formation of the molecular building blocks of life, occurring in the coldest, darkest places imaginable, long before a star has even ignited. The profound puzzle is mapping the precise reaction pathways. It is a chemical chain reaction conducted in ultra-slow motion over millions of years on a billion tiny surfaces. Which molecules form first? How do the more complex ones avoid being destroyed by the very cosmic rays that sometimes provide the energy to create them? We must simulate these alien conditions in labs on Earth, chilling chambers to near absolute zero and watching reactions unfold at a glacial pace, hoping to replicate the cryptic recipes of the cosmos. The significance of this dark chemistry cannot be overstated. When a part of the cloud finally collapses under gravity to form a new star and a swirling disk of planet-forming material, all these complex molecules are baked into the mix. They become part of comets, asteroids, and eventually the planets themselves. The water in your glass, the carbon in your cells, the sugars that power life, all began their journey as atoms clinging to specks of dust in a lightless cloud. The dark molecular clouds are not just cradles for stars. They are the silent kitchens where the galaxy prepares the raw ingredients for worlds and perhaps for life itself. What other complex compounds are being written in the dark, waiting for a star's light to read them? Yet within those dark chemical kitchens, a violent storm is always raging. The formation of a star is not a gentle fall, but a chaotic battle against a cosmic hurricane. This is the mystery of interstellar turbulence, and it presents a fundamental paradox. If gravity were the only force at work inside a molecular cloud, the process would be swift and devastatingly efficient. A cloud would simply collapse inward, fragmenting into countless stars, draining itself in a mere few million years. Our galaxy would have burned through its stellar fuel eons ago, leaving behind a dark, starless graveyard. But that is not what we see. Star formation is a slow, inefficient, and sporadic process. Only a tiny percentage of a cloud's mass ever turns into stars. Something is fighting gravity, holding it back, and stretching the timeline of stellar birth across millions of years. That something is supersonic turbulence. Imagine the gas inside these colossal clouds is not still, but churning like a pot of boiling water, only moving at speeds that dwarf the fastest hurricanes. Shockwaves crisscross the interior, creating a froth of dense knots and vast, empty voids. This chaotic motion creates a form of pressure, a relentless buffeting that counteracts the steady, inward pull of gravity. It keeps the cloud puffed up and prevents it from collapsing all at once. Gravity can only win in the deepest, densest pockets where the turbulent motions have cancelled each other out, allowing a knot of gas to finally fall inward on itself. So the central question becomes, what is stirring the pot? What cosmic engines are pumping energy into these clouds to keep this supersonic weather system alive? The prime suspects are the stars themselves in their most violent moments. When a massive star dies in a supernova explosion, it unleashes a cataclysmic shockwave that slams into nearby clouds, compressing some regions and shredding others, injecting a massive dose of chaotic energy. Similarly, the fierce stellar winds from young, hot stars can carve out vast bubbles and send ripples of turbulence through their surroundings. Even the gentle rotation of the galaxy itself, shearing clouds as they orbit, may contribute to the internal churn. This creates a fascinating feedback loop. Turbulence slows star formation, but the stars that do form then release energy that sustains the turbulence, which in turn regulates the birth of the next generation. It is a self-regulating cycle, a galactic heartbeat. Understanding this chaotic force is not just about solving a physics puzzle. It is the key to predicting the rhythm of a galaxy's life. Why do some galaxies blaze with newborn stars while others are quiet and serene? The answer lies in the balance between gravity's whisper and turbulence's roar. By learning the language of this interstellar weather, we can read the future of stellar populations and comprehend why our own Milky Way produces only a handful of new stars each year, a gentle simmer in a universe capable of a furious boil. What other invisible storms are shaping the destiny of cosmic structures? That chaotic turbulence is a death sentence for the delicate dust grains we began with. Their journey is a constant fight for survival, a cosmic balancing act between creation and destruction. This is the mystery of the dust budget, a simple question with a complex answer. How can something so fragile persist for billions of years? The forces arrayed against a dust grain are terrifying. Drift into a region of hot, ionized gas around a massive star, and you face sputtering. Individual atoms moving at ferocious speeds in the hot gas act like a microscopic sandblaster, knocking atoms right off the grain's surface, slowly eroding it into nothing. A supernova shockwave is far worse. The grain is hit by a wall of plasma moving at millions of miles per hour. The sheer friction from plowing through this dense, fast-moving gas can heat the grain instantly, vaporizing it completely. Even the gentle warmth of a newborn star is a threat. Venture too close, and the intense radiation will heat the grain until its molecules simply fly apart, a process called sublimation. Given the sheer violence of the interstellar environment, our models suggest dust should be annihilated on timescales far shorter than the age of the galaxy. Yet when we look out, we see dust everywhere, in ancient galaxies and newborn stellar nurseries alike. So how does it survive? The answer must lie in a constant, dynamic cycle of death and rebirth. This is the concept of interstellar dust recycling, A grain might be shattered in a shock wave, but its fragments, now individual atoms or small molecules, are not lost. They are simply returned to the gas phase, floating in the cloud. There, they can once again find their way to the surface of another, surviving dust grain, or even serve as the seed for a brand new one. It is a cosmic form of reincarnation where the material of one destroyed grain lives on in its descendants, but recycling alone might not balance the books. Astronomers are now investigating the possibility of rapid, efficient formation pathways that could constantly replenish the supply. Perhaps the cool, dense winds blowing from certain types of aging stars are ideal factories where atoms can quickly condense into grains before they ever escape the star's vicinity. Maybe the expanding ejecta of a supernova itself, as it cools from an unimaginable fireball, provides a perfect environment for dust to condense in enormous quantities, literally rising from its own ashes. Some observations of supernova remnants seem to show just that, clouds of fresh dust forming in the wreckage within mere decades. This turns our understanding on its head. The most destructive events in the universe might also be its most prolific creators. The persistent glow of dust across cosmic time is not a sign of delicate permanence, but of relentless, violent renewal. It is a testament to a galaxy that is constantly tearing itself apart and rebuilding, with every microscopic grain a survivor in an endless war. That fragile dust endures within a galaxy of scorching cavities. While the dark clouds are the cold, dense nurseries, much of interstellar space is actually filled with the opposite, a searing plasma known as the hot ionized medium. This is the galaxy's fever. Imagine the aftermath of a supernova, not just the brilliant flash, but the enduring consequence. The titanic explosion carves out a colossal cavity in the surrounding gas, a bubble of unimaginable heat that can expand for millions of years. Inside this bubble, the gas is not just warm, it is ionized, stripped of its electrons, and heated to temperatures of over 1 million degrees. This is not a localized phenomenon. So many supernovae have exploded over the Milky Way's lifetime that their bubbles overlap, creating a vast, frothy network of hot plasma that permeates the galactic disk, a Swiss cheese structure where the holes are made of fire. This hot phase is incredibly tenuous, with perhaps only a few thousand atoms in a volume the size of a cathedral. Yet, despite its ghostly thinness, it represents a major reservoir of the galaxy's normal matter, a significant portion of those missing baryons we searched for earlier. The central mystery of the hot ionized medium is one of endurance. How does this gas stay so blisteringly hot? In the vacuum of space, a hot gas should simply expand, cool down, and fade away relatively quickly. But the observations tell us it persists. The answer seems to be a constant reheating. While a single supernova bubble will eventually cool, new supernovae are always going off, reigniting the plasma, pumping fresh energy into the galactic atmosphere. It is a perpetual stoking of a cosmic furnace, but the real intrigue lies in how this scorching plasma interacts with its surroundings. Picture a blistering hot bubble pressing against the cold, dense wall of a molecular cloud. The interface is a front of incredible violence and complexity. The intense heat from the hot medium evaporates the outer layers of the cold cloud, stripping atoms away and dragging them into the plasma. This process, called thermal evaporation, is a crucial recycling mechanism. It takes the heavy elements locked up in cold clouds and injects them back into the hot phase, where they can eventually be incorporated into new generations of stars and planets. Conversely, the hot plasma can also trigger star formation. As a supernova bubble expands, its shockwave can slam into a quiescent cloud, compressing it violently. This compression can overwhelm the cloud's internal turbulence and magnetic support, triggering gravitational collapse and the birth of new stars. So the hot ionized medium is both a destroyer and a creator, a relentless force that erodes old structures and forges new ones. Its role in the galactic ecosystem is fundamental. It is the energetic circulatory system of the Milky Way, transporting energy and chemically enriched material across vast distances. By studying this elusive, searing phase, we are essentially taking the galaxy's temperature, trying to understand the fever that shapes its evolution and drives the endless cycle of stellar life and death. What other secrets are hidden within these invisible bubbles of million-degree fog? That scorching plasma is a world of lonely atoms, but the story of the galaxy is written by partnerships. At the heart of every dark molecular cloud, the primary actor is not an atom but a molecule. It is the simplest partnership in the cosmos, two hydrogen atoms bound together. This is molecular hydrogen, H2, and its formation is the first quiet step toward building a star. Yet this seemingly simple handshake is shrouded in a profound and practical mystery. In the diffuse emptiness of space, two lone hydrogen atoms are terrible at forming a bond. When they collide, they simply bounce off each other. The problem is physics. To form a stable molecule, the two atoms need to shed the tiny bit of energy from their collision. In the near-perfect vacuum of the interstellar medium, there is nothing around to carry that energy away. It is like trying to clasp your hands while they are covered in slippery oil. The grip simply will not hold. So how does the most abundant molecule in the universe actually form? It needs a matchmaker, a solid third body to facilitate the introduction. That matchmaker is once again a tiny grain of interstellar dust. Here is how the cosmic chemistry works. A single hydrogen atom drifts through the dark and by chance sticks to the cold surface of a dust grain. It sits there, absorbed, waiting. Then, a second hydrogen atom arrives and sticks nearby. Now, on the surface of this microscopic platform, the two atoms are close enough to interact. They can shuffle across the grain's surface, meet, and link together. The dust grain itself acts as the crucial third body, absorbing the excess energy of the bond and allowing the new H2 molecule to stabilize. Once formed, the weak forces holding it to the grain are overcome, and the molecule is released back into the gas, ready to become part of a star-forming cloud. This process seems straightforward, but the efficiency is everything, and it is here the mystery deepens. How quickly does this happen on different types of dust grains? A grain made of carbon might facilitate the reaction differently than a grain made of silicate rock or coated in a layer of water ice. The temperature of the grain is critical too. Too warm and the hydrogen atoms never stick. Too cold and they might get trapped in an icy matrix, unable to move and find each other. The environment is also key. In the harsh ultraviolet light of interstellar space, a newly formed H2 molecule can be easily torn apart by a photon. So the formation must happen in the shielded hearts of clouds or on the dark sides of dust grains where the chemistry is protected. Astronomers run complex computer models and lab experiments trying to pin down the exact rates of this fundamental reaction. Why does this microscopic detail matter so much? Because molecular hydrogen is the primary coolant for a collapsing cloud. Atomic hydrogen is not very efficient at radiating away heat, but when two atoms form a molecule, they can vibrate and rotate, releasing energy in the form of infrared light. This allows a cloud that is beginning to collapse under gravity to shed its heat. As it cools, the internal pressure drops and gravity can win more easily, accelerating the collapse into a protostar. The rate at which H2 forms directly dictates when a cloud becomes unstable and how quickly it fragments into stars. Get the formation rate wrong in your models, and your predictions for star formation across the galaxy become untethered from reality. The entire timeline of galactic evolution, the rhythm of stellar birth, hinges on the quiet, fragile partnership of two hydrogen atoms meeting on a speck of dust in the dark. It is the universe's most important secret handshake. The most important partnership in the cosmos begins with a simple handshake, but the chemistry of the dark does not stop there. In the frigid depths of those same molecular clouds, astronomers have uncovered a scent. It is the aroma of rum and raspberries, a fragrance drifting between the stars. This is no poetic metaphor. It is the chemical signature of ethyl formate, a complex organic molecule, one of hundreds now detected in the interstellar medium. Even more profound, we have found glycine, the simplest amino acid, in the gas around comets and within star-forming regions. These discoveries shatter our old view of space as a sterile void. The building blocks of life, it seems, are being manufactured in the cosmic dark. This presents a magnificent contradiction. How can these large, delicate organic structures possibly assemble and endure in an environment bathed in destructive ultraviolet radiation and pummeled by cosmic rays? The molecules of life are fragile. On Earth, they are protected by an atmosphere and a magnetic field. In open space, they should be torn apart by photons in an astronomical instant. Their very existence tells us the interstellar medium is far more clever and protective than we ever imagined. There are two leading theories for how this miracle of cosmic chemistry occurs, and both center on the humble dust grain. The first is known as surface chemistry on icy mantles. Picture a dust grain not as a bare speck of rock, but as a tiny ice-covered pebble. In the extreme cold of a dense cloud, water vapor, along with molecules like carbon monoxide and ammonia, freezes onto the grain's surface, building up a microscopic mantle of ice. This icy shell becomes a bustling chemical laboratory. As atoms and simple molecules land on this frozen matrix, they gain the mobility to slide around and meet. Crucially, the ice itself shields them from the worst of the external radiation. Within this frozen sanctuary, cosmic rays or ultraviolet photons penetrating the outer layers of the cloud can actually provide the energy needed to drive reactions, breaking and forging bonds between the trapped molecules. Step by step, on the surface of 1,000,000 billion of these icy grains, complexity grows. Simple ices are transformed into more complex organics, like ethanol or even that rum-scented ethyl formate. When a young star finally ignites nearby, its warmth sublimates the icy mantles, releasing this rich cocktail of probiotic molecules into the surrounding gas where our telescopes can detect them. The second theory argues for a more direct path, formation right in the gas phase. Proponents suggest that in the slightly warmer, denser regions of clouds, ion-molecule reactions could build complexity without needing a solid surface. A molecule loses an electron, becoming a reactive ion. This charged particle then attracts and readily bonds with other passing neutrals, building larger structures in a cascade of gas phase collisions. This process might be especially efficient for creating some of the linear carbon chain molecules we see in space. The truth likely involves both pathways, a symphony of chemistry on grains and in the gas, each contributing to the interstellar zoo of molecules. The implications of this discovery ripple far beyond chemistry. It fuels the ancient idea of panspermia, not in the dramatic sense of fully formed life riding on comets, but in a far more plausible and powerful form, molecular panspermia. This theory posits that the fundamental building blocks of life, amino acids, sugars, the components of DNA, are ubiquitous products of cosmic chemistry. They are forged in interstellar clouds, packaged into comets and asteroids during planetary system formation, and then delivered to young worlds like early Earth via impacts. Our planet may not have had to invent life's ingredients from scratch. Instead, it may have been seeded with a starter kit from the stars, a gift from the interstellar medium. If that is true, then the chemical pathway to life is not a rare, freak accident, but a natural and common outcome of galactic evolution. The scent of rum in the void is more than a curiosity. It is a whisper that the universe is inherently organic, and that the raw materials for biology are sewn into the fabric of space itself, waiting for a warm, watery world to begin the next chapter. That cosmic scent of rum drifts through an architecture of astonishing complexity. The interstellar medium is not a simple collection of isolated clouds floating in an empty void. Its true structure is far more chaotic and interconnected, a revelation that forms our 12th mystery. Is the galaxy filled with discrete, billowing clouds, or is it one continuous, frothing substance? Modern observations point decisively to the latter. The interstellar medium is a fractal foam, a cosmic sponge. Picture a vast sea of hot, ionized plasma, the result of overlapping supernova bubbles. Within this searing froth, threads and filaments of warm gas condense like dew on a web, and embedded within those threads are the dense, cold knots we recognize as molecular clouds. They are not isolated islands, but the densest peaks in a continuous, turbulent landscape. This means there are no true walls separating the phases of the interstellar medium. Instead, there are gradients and interfaces. A cold cloud does not simply end, it evaporates into a warm haze, which then diffuses into the hot plasma. Corridors and tunnels of warmer gas likely weave through the dense regions, creating a labyrinthine structure. This topology is critical because it dictates how everything moves. Radiation from a hot star does not travel in a straight line until it hits a cloud. It filters through this porous, frothy medium, being absorbed and re-emitted, its path twisted by the ever-changing density. Cosmic rays do not fly unimpeded across thousands of light years. They are channeled and scattered by this magnetized foam, their journey a random walk through a galactic maze. Even the flow of matter itself, the gas that will one day become stars, is guided by this architecture. The great mystery is what determines the shape and scale of this interstellar sponge. What sets the size of the bubbles and the thickness of the filaments? The answer appears to be a dynamic, three-way tug of war. Supernovae are the primary sculptors, blowing the giant bubbles that create the frothy backdrop. Their shockwaves compress gas into sheets and filaments while also tearing other structures apart. But magnetic fields act as a restraining skeleton. They lend strength to the gas, resisting complete disruption and helping to shape the filaments into long, coherent strands. They guide the flow of material, perhaps helping to funnel gas along specific pathways to feed growing clouds. And finally, turbulence is the relentless stirrer. It tangles the magnetic fields, it shreds smooth surfaces into fractal complexity, and it determines how efficiently energy cascades from the large scales of supernova bubbles down to the small scales where stars finally form. This interplay creates a self-similar structure where patterns of bubbles within bubbles and filaments branching into smaller filaments appear at every scale we look. Understanding this architecture is not just a descriptive exercise, it is the key to building accurate models of our galaxy. To predict how a shockwave propagates, how a cloud evaporates, or how cosmic rays diffuse, we must first simulate the sponge. The difference between a model with discrete clouds and one with a continuous froth can be profound. In the frothy model, everything is connected. A supernova in one spiral arm can influence the chemistry and pressure in a cloud halfway across the galaxy, not through a direct blast, but through the slow percolation of energy and waves through the interconnected network. The galaxy breathes as a single entity, its lungs a froth of glowing plasma and dark dust. The voids are as important as the knots, for they are the channels through which the galaxy's energy flows. This means the emptiness between the stars is not empty at all. It is a structured, dynamic, and living medium, its topology holding the secret to the rhythm of cosmic evolution. What other galactic processes are hidden within the geometry of this infinite sponge? The architecture of that cosmic sponge is built from particles no larger than a virus, yet each one carries a hidden electric charge. This is the microphysics of interstellar dust, and it transforms these passive specks into active players. A dust grain drifting in space is rarely electrically neutral. It exists in a constant storm of charging and discharging, a microscopic drama with galactic consequences. The primary charger is starlight itself. When a photon of ultraviolet light carrying more energy than visible light strikes a dust grain, it can knock an electron clean off the surface. This process, called photoelectric emission, leaves the grain with a net positive charge. It is a tiny theft happening quadrillions of times a second across the galaxy. But there are other forces at work. In hotter regions filled with plasma, fast-moving electrons and ions constantly collide with grains. Electrons, being lighter and faster, hit more frequently, often sticking and giving the grain a negative charge. In the dense, dark hearts of molecular clouds where starlight cannot penetrate, the charging is dominated by these collisions with the ambient plasma and even by sticking of charged atoms from the gas. The result is a dynamic equilibrium, a grain's charge flickering between positive, negative, and neutral as conditions change around it. This seemingly esoteric detail is a master switch for the behavior of the entire interstellar medium. A charged dust grain is no longer just a piece of floating debris, it is a magnetized particle. It becomes intimately coupled to the galaxy's invisible magnetic field. The Lorentz force, the same effect that guides a charged particle in a laboratory experiment, now acts on the grain. A charged grain will tend to spiral along magnetic field lines, its motion constrained by the invisible web. This has a profound effect on the dynamics of gas clouds. The dust is mixed with the gas, and through frequent collisions, it drags the gas along with it. This means the magnetic field, by controlling the charged dust, can indirectly break the motion of the entire cloud, affecting how it rotates, how it collapses, and how it fragments. In the delicate balance between gravity and support that determines star formation, the charge on a dust grain becomes a critical variable in the equation. The central mystery is predicting the precise charge on any given grain at any given time. It is not a simple number. The charge depends on a dizzying array of factors. The size of the grain matters enormously. A larger grain has more surface area to absorb charging particles or emit electrons, but it also has a greater capacity to hold charge. Its composition is crucial. A graphite grain, which is a conductor, will distribute charge evenly and may emit electrons more easily than an insulating silicate grain, which can develop patchy, localized charges. The local environment is everything. The intensity and color of the ambient starlight, the density and temperature of the surrounding plasma, even the presence of other charged grains all feed into a complex, ever-changing calculation. Astronomers must use sophisticated models to estimate a charge distribution, a statistical picture of how many grains are at what charge level in a particular cloud. Getting this wrong can throw off our understanding of fundamental processes. For instance, the beautiful polarization of starlight that reveals magnetic fields relies on the alignment of these needle-like grains. That alignment is driven by a subtle interplay between magnetic forces, gas collisions, and the grain's own rotation, all of which are exquisitely sensitive to its electric charge. If we misjudge the charge, we misread the magnetic field map. Furthermore, this micro-scale charge dictates macro-scale chemistry. On the surface of a positively charged grain, it will attract and more readily bind negative ions or electrons from the gas, altering which chemical reactions are possible. A negatively charged grain will attract positive ions. The charged state of the dust essentially sets the menu for surface chemistry, influencing which complex organic molecules can form in the dark. So the humble dust grain, through the invisible spark of its electric charge, becomes a nexus point. It links the radiation field of stars to the magnetic skeleton of the galaxy, and it directs the chemical pathways that may lead to life. A change in starlight 1 million years ago could have altered the charge on 1 billion grains, which in turn affected how a cloud collapsed, what molecules it forged, and what kind of star system it eventually became. The universe is connected by threads we are only beginning to see, and some of the most powerful are woven from the static cling of microscopic dust. That microscopic static cling is part of a grander galactic-scale pulse. The interstellar medium is not a passive backdrop, but the beating heart of the Milky Way itself. It is the great regulator of galactic evolution. Zoom out to a galaxy-wide perspective, and the central mystery becomes clear. How does this chaotic, multiphase sea actually control the life and death of an entire galaxy? The answer lies in a delicate cosmic-scale balancing act between creation and destruction. The interstellar medium serves two primary, opposing roles. First, it is the vast reservoir for star formation, the cold, dense fuel that gravity will ignite into new suns. Second, and just as crucially, it is the repository for stellar waste. When stars live and die, they do not vanish. They transmute elements. A star like our Sun spends its life fusing hydrogen into helium. More massive stars go further, forging carbon, oxygen, nitrogen, and iron in their cores. In their final, violent acts as supernova, they create even heavier elements like gold, silver, and uranium. All these newly forged atoms are blasted back into the interstellar medium, enriching it. The gas that once formed a first-generation star, composed almost purely of hydrogen and helium from the Big Bang, is now seeded with the heavy elements, the metals, necessary to form rocky planets and ultimately life. This means the galaxy is not a static entity. It is a giant, slow-motion recycling plant. One generation of stars dies, polluting the nursery with the ashes of its creation. The next generation of stars forms from this enriched material, born with a richer chemical heritage. Our own Sun is a product of this process, a third or fourth generation star whose planets are built from stardust forged in the hearts of long-dead giants. But this beautiful cycle contains a paradox, and this is where the greatest unanswered questions lie. The process of star formation is not simply a one-way drain on the gas reservoir. The stars themselves, especially the most massive and violent ones, give back energy and momentum to the medium that birthed them. Astronomers call this galactic feedback, and it is the most powerful, yet least understood, force shaping a galaxy's destiny. Imagine a cluster of massive stars igniting within a giant molecular cloud. Their fierce ultraviolet radiation and powerful stellar winds act like a cosmic blowtorch, heating the surrounding gas, evaporating it, and carving vast cavities. This feedback can actually halt further star formation in that local region by dispersing the very cloud that was giving it birth. On an even more dramatic scale, when these massive stars finally explode as supernova, their combined shockwaves can blow gigantic holes in the galactic disk, potentially driving gas out of the galaxy entirely or heating the remaining medium so much that it cannot cool and form new stars. The most extreme feedback may come from the supermassive black hole at the galaxy's center. When it actively feeds, it can unleash jets and radiation so powerful they can heat the interstellar medium across the entire galaxy, effectively shutting down star formation on a global scale. This creates a critical, unresolved puzzle. How does a galaxy balance this feedback? Why does our Milky Way continue to form a few new stars each year in a gentle simmer, while other galaxies, called ellipticals, have had their star formation completely quenched, leaving them as red and dead collections of ancient stars? The details of this feedback loop, the precise mechanisms and efficiencies, remain one of the grand challenges in astrophysics. It is the mystery of galactic self-regulation. Too little feedback and a galaxy would convert all its gas into stars in a frantic burst, burning out quickly. Too much feedback and it starves itself, cutting off its own future. The interstellar medium is the arena where this battle is fought. Its state, whether it is cold and dense or hot and diffuse, is the direct result of this ongoing conflict between gravity's pull and stellar fury. The cycle of birth, death, and recycling is the true heartbeat of a galaxy, and we are still learning to decipher its rhythm. Does this mean a galaxy's fate is written in the temperature of its hidden ocean? That galactic heartbeat is measured by a single, fragile atom. Hidden within the vast sea of interstellar hydrogen is a special variant, a heavier cousin called deuterium. This is not just another element, it is a cosmic fossil. Every single deuterium nucleus in the universe was forged within the first few minutes after the Big Bang, in that brief, searing window of primordial nucleosynthesis. No star, no supernova, no process we know of creates significant new deuterium. Stars only destroy it. When deuterium is pulled into a star, the intense heat and pressure at the core quickly fuse it into heavier elements like helium-3. It is a one-way trip. This makes deuterium the perfect cosmic gauge. The amount of deuterium left in the interstellar gas should tell us, with beautiful simplicity, how much of the original primordial gas has been cycled through stars and processed. More processed gas means less deuterium. It is a direct measurement of the galaxy's chemical history, but when astronomers point their telescopes to measure this crucial ratio, the numbers tell a confusing, contradictory story. The mystery of interstellar deuterium is that its abundance is all over the map. Look along one line of sight to a distant star, and you might measure a deuterium to hydrogen ratio that matches pristine Big Bang predictions. Look in a different direction through what seems like similar gas, and the measured deuterium can be half that amount or even less. This wild variation makes no sense if the interstellar medium is well mixed. It suggests pockets of gas that have never been inside a star sitting right next to regions that have been processed multiple times over, with little blending between them. Even more puzzling, when astronomers try to calculate a galaxy-wide average, the overall deuterium abundance seems lower than what the most precise models of the Big Bang predict. So where did the missing deuterium go? One possibility is that our understanding of the Big Bang itself needs refinement. Perhaps the primordial deuterium production was slightly lower than we think. But the cosmic microwave background measurements are so precise that this seems unlikely to be the full answer. The more compelling explanations lie in the complex choreography of the interstellar medium itself. Perhaps deuterium is not just destroyed in stars, but also in other places we have not fully accounted for. Could it be destroyed in the hot, turbulent interfaces between different phases of the interstellar medium, or in the powerful shocks from stellar winds? Maybe deuterium atoms are preferentially locked away in forms we struggle to detect. While we measure deuterium by looking at its absorption of ultraviolet light from distant stars, that method only sees deuterium in its atomic form. What if a significant fraction of it has instead bonded to form heavy water or other deuterium-bearing molecules and frozen onto the surfaces of dust grains? This deuterium-enriched ice would be invisible to our standard ultraviolet measurements, effectively hiding the fossil in plain sight. Another fascinating idea involves the galactic cycle itself. When massive stars die and enrich the medium, they also inject enormous energy. This could drive fountains of hot gas out of the galactic disk, carrying away a deuterium-poor mixture. Meanwhile, fresh, deuterium-rich gas might be constantly raining down onto the galaxy from the vast circumgalactic medium, the halo of gas that surrounds the Milky Way. The ratio we measure locally would then be a snapshot of this ongoing inflow and outflow, not a simple average. Solving the deuterium puzzle is crucial. It is the key to calibrating the entire story of galactic chemical evolution. If we cannot accurately account for this one simple fossil, how can we trust our models for the production and distribution of all the other elements? The varying signal of deuterium is a stark reminder that the interstellar medium is not a well-stirred soup, but a layered, segregated archive. Its pages are stuck together, some pristine, others heavily annotated by stellar lives. Reading this archive requires understanding not just the writing, but why some pages are so stubbornly kept apart from the rest. Deuterium's hidden story is a clue that our galactic inventory is still incomplete. We have mapped the glowing gas and the dark clouds, but what if an entire population of cosmic fuel has been hiding in plain sight, or more accurately, in dark sight? This brings us to the ghost in the machine, the mystery of dark gas. Picture a vast reservoir of molecular hydrogen, the primary fuel for stars drifting through the galaxy. Normally, we find this H2 by looking for its faithful companion, carbon monoxide. Carbon monoxide molecules, when jostled by collisions in a dense cloud, emit a very specific radio wavelength that our telescopes easily pick up. It has been our standard tracer, our beacon for finding star-forming material for decades. But what if that partnership is not universal? Astronomers made a startling discovery by looking at the sky in a completely different way, not with radio eyes but by detecting gamma rays. Our galaxy is faintly glowing in high-energy gamma radiation, produced when cosmic rays, those high-speed atomic bullets, collide with the nuclei of atoms in interstellar gas. By meticulously mapping this gamma-ray glow and subtracting the contribution from atomic hydrogen, which we can see with radio telescopes, researchers found an excess. There was gamma-ray emission coming from places where our maps of atomic hydrogen showed nothing. The only explanation was an unseen mass of molecular hydrogen, vast clouds of H2 that were not singing out in the familiar carbon monoxide radio line. They were dark to our traditional surveys. This dark gas is molecular hydrogen without its carbon monoxide tracer. The reason for this missing partner is a fascinating chemical puzzle. Carbon monoxide is fragile, easily destroyed by ultraviolet radiation. In the outer, less dense envelopes of molecular clouds, or in clouds that are just beginning to coalesce, the ultraviolet light from distant stars can penetrate deeply enough to break apart CO molecules, while leaving the heartier H2 molecules intact. In these transitional regions, you have a cloud of pure molecular hydrogen, invisible to radio telescopes tuned to carbon monoxide. It is a shadow universe of star-forming fuel, detectable only by the indirect flash of cosmic ray collisions or by extremely subtle signatures of the H2 itself in the far infrared. The existence of dark gas forces a monumental question. Just how much of it is out there? Current estimates suggest it could account for a significant fraction, perhaps up to 30%, of the entire molecular gas content of the Milky Way. If true, this means we have been systematically underestimating the amount of raw material available to form new stars and planets. Our galactic ledger, the balance sheet of cosmic mass, has a major column missing. Its distribution is another enigma. Does it lurk primarily on the fringes of known clouds as a protective cocoon around the CO bright cores? Or does it form entirely separate, vast structures, a hidden skeleton of the galaxy's spiral arms? Understanding why dark gas lacks carbon monoxide is more than a chemical curiosity. It is a window into the earliest stages of cloud formation and destruction. These may be the birth cradles of clouds or their dying breaths, regions where the interstellar medium is in a state of transition. Finding and mapping this invisible component is like turning on a blacklight in a dark room, revealing patterns and structures we never knew were there. It reminds us that the universe often hides its most important secrets not in the brilliant light, but in the profound silence between the frequencies we know how to hear. What other invisible landscapes are waiting to be revealed by the collisions of unseen bullets? The dark gas is a reservoir of cold potential, but its ultimate fate is decided by a hidden battle over a single, fundamental property: temperature. The interstellar medium exists in a state of perpetual thermal conflict, a cosmic tug of war between heating and cooling. This is not a simple story of hot and cold, but a dynamic, localized struggle that dictates the very nature of the galactic sea. The temperature of a parcel of interstellar gas determines everything. Will it remain a hot, diffuse plasma, a warm atomic fog, or will it cool into a cold, dense molecular cloud ripe for star formation? The outcome hinges on a precise balance between energy in and energy out, a thermostat we are still struggling to read. The heating agents are numerous and violent. The primary source is starlight, especially the fierce ultraviolet radiation from massive young stars. These high-energy photons do not just illuminate, they ionize, stripping electrons from atoms and injecting kinetic energy that translates directly to heat. Cosmic rays, those relentless high-speed particles, provide another pervasive heat source. As they tear through the gas, they ionize atoms and molecules, and the secondary electrons they liberate carry enough energy to heat their surroundings. Even the supersonic turbulence churning through clouds acts as a heater. When those chaotic motions dissipate, much like the energy of a stirred cup of coffee eventually warming the cup, they transfer their kinetic energy into thermal energy of the gas. Supernova shockwaves are the ultimate heating events, blasting regions to millions of degrees in an instant, but the universe is always trying to cool down. For every heating mechanism, there is a cooling process, a way for the gas to shed energy and radiate it away into the void. This is where the chemistry of the gas becomes critical. Atomic hydrogen, the most abundant element, is a poor radiator, but when it collides with other atoms or free electrons, it can be excited and then release a faint photon of ultraviolet light, carrying away a tiny bit of heat. More efficient coolants are molecules and metals. Carbon monoxide, that common tracer, is a superstar coolant. Its rotational lines, like a spinning ice skater throwing off energy, allow it to radiate efficiently in the infrared, helping dense clouds shed heat and collapse. Even trace amounts of heavier elements like oxygen, carbon, and iron, sprinkled through the gas from ancient supernova, provide crucial cooling pathways through a forest of faint emission lines. The great thermodynamic mystery is that the observed temperatures in many regions defy our simple models of equilibrium. If heating and cooling were in perfect local balance, we should be able to predict the temperature of a cloud if we know its density and the local radiation field. Yet time and again, measurements surprise us. Some diffuse clouds are warmer than they should be, while some dense cores are colder. This tells us the balance is not static but dynamic and often non-local. The heat from a distant supernova might be propagating through the frothy medium, warming a cloud from the outside while its interior desperately tries to cool. Or the complex structure of the gas itself, its fractal sponge-like nature, means some parts are shielded from heating while others are exposed, creating a patchwork of temperatures within a single structure. This delicate thermal balance is the ultimate gatekeeper for star formation. For a cloud to collapse and form stars, it must cool significantly. Gravity can only overcome internal pressure if that pressure drops, and pressure is directly tied to temperature. A cloud bathed in too much ultraviolet light will stay warm and puffed up, resisting collapse. But if enough cooling molecules like carbon monoxide can form, and if the cloud can shield itself from the harshest radiation, it can radiate its heat away. As it cools, the pressure drops, the cloud contracts, and gravity gains the upper hand. The transition from warm atomic gas to cold molecular cloud is fundamentally a thermal phase change, driven by this intricate dance between heating and cooling agents. We are still trying to calibrate this cosmic thermostat. The models are fiendishly complex because every process is interconnected. The heating influences the chemistry, which determines the cooling, which changes the density, which then affects how efficiently heating and cooling work. It is a feedback loop of astonishing subtlety. A slight overestimate of cosmic ray heating or an underestimate of metal line cooling can throw off an entire simulation of galactic evolution. The temperature of the interstellar medium is more than a number. It is the result of a billion local decisions made by photons, particles, and atoms. It is the thermal fingerprint of the galaxy's history, and learning to read it is key to predicting when new stars will ignite in the silent dark. That cosmic thermostat is measured by the faintest of glows, a whisper of heat that was once considered nothing more than static. As cosmologists trained their instruments on the most ancient light in the universe, the cosmic microwave background, they encountered a persistent nuisance. A faint, mysterious fog of microwave emission seemed to cling to our own galaxy, obscuring their pristine view of the Big Bang's afterglow. This was not the signal they sought, but a local ghost. They named it anomalous microwave emission, or AIM, and its origin became a puzzle that would tie directly back to the dusty heart of the interstellar medium. This glow is not like the radio waves from spinning electrons or the infrared heat from warm dust. It occupies a specific, poorly understood niche in the spectrum, a hum that had no clear explanation for years. The breakthrough came when astronomers realized this emission correlated perfectly with clouds of interstellar dust, particularly in regions illuminated by starlight. The ghost had a physical address. The leading theory is both elegant and bizarre. The emission likely comes from the tiniest denizens of the dust family, nanoparticles smaller than a virus spinning at dizzying speeds. Think of a grain of dust so small it contains only a few thousand atoms. When it absorbs a single photon of starlight, that tiny packet of energy is enough to set it spinning at rates of billions of revolutions per second. This frantic rotation causes the grain to emit radiation in the microwave band, a process called electric dipole emission. It is like a trillion microscopic radio transmitters, each one a speck of dust humming its own frantic tune. But the exact identity of these spinning tops remains unknown. What are these nanoparticles made of? One strong candidate is a class of large carbon-based molecules known as polycyclic aromatic hydrocarbons, or PAH. These are essentially flat flakes of carbon and hydrogen, like tiny pieces of graphene or soot. They are known to exist abundantly in space, and their size and structure make them perfect candidates to spin rapidly when hit by light. Another, even more exotic possibility involves diamond-like grains. Imagine nanoparticles of carbon arranged in a crystalline structure, essentially nanodiamonds, forged in the atmospheres of carbon-rich stars or in the shocks of supernovae. These could also possess the right properties to produce the anomalous glow. The quest to identify the true carrier is a detective story played out across the electromagnetic spectrum. Astronomers search for the unique infrared fingerprints of these candidate molecules in the same clouds that produce the strong AMI signal, looking for a perfect correlation. Laboratory scientists try to recreate the conditions of space to measure the microwave spin of synthetic PAHs or nanodiamonds. Pinpointing the source is crucial for two profound reasons. First, it would solve a fundamental piece of interstellar microphysics. These nanoparticles represent a major but poorly understood component of cosmic dust. They are likely a key reservoir of cosmic carbon and could play an outsized role in surface chemistry and the shielding of molecular clouds. Understanding their nature and abundance would fill a major gap in our model of the galactic ecosystem. Second, and perhaps more urgently, solving the AMI mystery is essential for cosmology. To see the subtle patterns in the cosmic microwave background that tell us about the universe's infancy, scientists must subtract every possible contaminating foreground signal. Anomalous microwave emission is one of the last major foregrounds with significant uncertainty. If we do not know exactly what causes it or how it varies across the sky, we cannot clean our maps perfectly. Any residual noise could be misinterpreted as a feature of the early universe, potentially leading us astray in our understanding of dark energy, inflation, or the nature of the cosmos itself. So this faint galactic static is a barrier between us and the dawn of time. By learning to silence the hum of our own galaxy's spinning dust, we can finally hear the true whisper of creation. What other secrets are disguised as mere noise in the channels of the cosmos? The faint hum of spinning dust is the sound of a galaxy processing its own history. Every speck contains atoms forged in stellar furnaces, and their journey across the light years forms a profound mystery. How do the heavy elements, the metals like oxygen, carbon, and iron, travel from their violent births to the quiet corners where planets form? A supernova explosion is a spectacular but local event. It scatters its enriched debris into a hot, expanding bubble, a chemical island in the vast sea of primordial hydrogen and helium. For these life-critical elements to become part of new stars and worlds, they must escape that bubble and mix into the broader interstellar medium. This is the grand problem of galactic transport. Does the turbulence of the interstellar foam churn and spread these elements evenly, like cream stirred into coffee? Or do they remain in stubborn pockets, creating regions of the galaxy that are chemically rich while others remain pristine deserts? The evidence from our own Milky Way presents a confusing picture. We observe clear metallicity gradients. This means that if you travel from the inner galaxy toward the outer spiral arms, the overall abundance of heavy elements steadily decreases. Stars and gas in the crowded galactic center are metal-rich, having been cycled through many generations of short-lived massive stars. Out in the quieter suburbs, the material is more primordial, less processed. This gradient suggests that mixing is inefficient over galactic scales. The chemical enrichment seems to happen locally and then slowly diffuse outward, perhaps carried by the gentle radial flow of gas or by the migration of stars themselves. But within this broad trend, the details are chaotic. In any given spiral arm, you can find stars of vastly different metallicities sitting relatively close together. This indicates that the interstellar medium is not a well-blended smoothie. Instead, it is a chunky stew where pockets of older, metal-poor gas can survive for billions of years alongside veins of recently enriched material. The mechanisms for even limited mixing are incredibly complex. Supernova bubbles can blow holes in the galactic disk, sometimes breaking out and venting their metal-rich gas high above the plane. This gas then cools and falls back down in a galactic fountain, raining enriched material over a wider area. Spiral density waves, the grand patterns that define the arms, can also shuffle gas around, stirring the pot on a massive scale. Yet, the persistence of the metallicity gradient tells us this stirring is gentle and incomplete. The galaxy remembers its history in its chemistry. This transport puzzle is not just about mapping ingredients, it is about the very recipe for planets like our own. Earth is built from a specific mix of elements: silicon, iron, oxygen, carbon. For a rocky, life-bearing world to form, its parent star must have formed from a cloud that was enriched to just the right level. Too few metals and you get a gas giant with no solid core. Too many, and the dynamics of planet formation might be disrupted. The journey of a single iron atom from the core of a dying star to the crust of a planet is an epic voyage spanning billions of years and countless light years. It must survive being blasted into space, avoid falling into a black hole, condense onto a dust grain, survive the collapse of a new solar nebula, and finally accrete into a world. The fact that we are here, made of such stardust, is proof that this transport, however messy and inefficient, ultimately works. But the path it took and the timescales involved remain written in the faint chemical signatures of stars across the Milky Way, a scattered diary we are still learning to read. That chemical journey across the galaxy often ends with a cataclysm. A supernova remnant is the universe's most violent sculptor, and its interaction with the interstellar medium is a masterclass in cosmic chaos. When a massive star exhausts its fuel, its core collapses in a fraction of a second, triggering an explosion that outshines an entire galaxy. The outer layers are blasted outward at speeds exceeding 10% the speed of light, a supersonic shockwave of stellar debris. This is not an explosion in a vacuum, it is a bomb detonated in an ocean. The shockwave plows into the surrounding interstellar medium, a wall of fire meeting a fog of gas and dust. The collision creates a fleeting, high-energy laboratory, a natural particle accelerator and furnace where we can witness physics under the most extreme conditions imaginable. The first puzzle is one of efficiency. The supernova unleashes an almost inconceivable amount of energy, equivalent to the Sun's entire lifetime output released in a single brilliant flash. But how much of that titanic energy is actually transferred to the interstellar medium? The shockwave does two things. It sweeps up the ambient gas, piling it into a dense, bright shell that we see as the beautiful filamentary nebula. And it heats the gas to millions of degrees, causing it to glow in X-rays. Yet, observations suggest the process is messy and inefficient. A significant portion of the energy might be lost to neutrinos during the collapse, or it might simply radiate away as light before it can push on the gas. Some energy might escape by blowing a hole clear through the galactic disk, venting hot gas out into the halo. Measuring the true mechanical punch of a supernova is critical for understanding how these events stir and heat the galactic pot. The second great question is whether this violence is creative or destructive. Does a supernova remnant trigger new star formation, or does it snuff it out? The answer, fascinatingly, is both. It all depends on timing and environment. In its earliest, most violent phase, the expanding shockwave can be utterly devastating. It can rip apart a nearby molecular cloud, tearing it apart with turbulent fury and evaporating its gas, effectively sterilizing a region of future stellar births. But as the remnant ages over tens of thousands of years, it slows down. The shock front becomes a more gentle, compressive wave. When this slower-moving wall of pressure encounters a dense cloud, it can squeeze it. This compression can overwhelm the cloud's internal support, tipping the balance in favor of gravity and triggering the collapse of new stellar seeds. We see evidence of this in places where young star clusters are found on the rims of old, expanding supernova shells. The remnant becomes a cosmic snowplow, gathering material into a dense, fertile ridge where the next generation can take root. The third, and perhaps most profound, puzzle happens right at the shock front itself. This is where we believe the majority of galactic cosmic rays are born. The theory is called diffusive shock acceleration. Picture the chaotic boundary where the supersonic ejector slams into the stationary interstellar gas. It is a region of tangled magnetic fields and incredible turbulence. A charged particle, a proton or an electron, can get caught in this maelstrom. It bounces back and forth across the shock front, trapped by magnetic mirrors, gaining a little speed with each crossing. Over time, it is whipped to relativistic velocities, becoming a cosmic ray bullet. But the precise mechanism is devilishly complex. How are particles injected into this acceleration process in the first place? How do the magnetic fields become amplified to such incredible strength right at the shock? Observations of supernova remnants in gamma rays, the light produced when cosmic rays interact, provide tantalizing clues, but a complete picture of this natural accelerator still eludes us. By studying these titanic collisions, we are not just watching stellar death. We are observing the primary engine of galactic feedback. Supernova remnants are the great recyclers and regulators. They disperse enriched material, they stir the interstellar soup, they heat the galactic atmosphere, and they potentially plant the seeds for new stars. They connect the life cycle of stars to the ecology of the entire galaxy. In the violent aftermath of a star's death, we find the forces that write the future of everything around it. But those supernova remnants are not the only source of fresh material raining down on the galactic disk. Far above the starry plane of the Milky Way, ghostly fleets of gas are sailing through the darkness. These are the high-velocity clouds, and their very existence challenges our understanding of the galaxy's boundaries. Picture vast structures, some spanning thousands of light-years, composed primarily of neutral hydrogen. They drift in the galactic halo, the sparse outer atmosphere of the Milky Way. What makes them truly strange is their motion. They are moving at speeds that have nothing to do with the orderly rotation of the galaxy's disk. Some are streaking inward at hundreds of kilometers per second, as if falling from a great height. Others seem to be on odd, looping orbits, they are interlopers from a realm we are only beginning to map. The central mystery is their origin. Where did these colossal clouds come from, and what force set them on their peculiar paths? Astronomers have several compelling and competing theories. One idea is that they are primordial fossils, leftovers from the very formation of the Milky Way itself. In this scenario, when our galaxy coalesced from the cosmic web billions of years ago, not all of the gas collapsed smoothly into the disk. Some clumps may have been left behind in the halo, taking eons to slowly spiral inward. They are ancient relics finally arriving at the party long after it started. A second, more violent theory points to our galaxy's cannibalistic nature. The Milky Way is surrounded by smaller satellite galaxies like the Large and Small Magellanic Clouds. As these dwarfs swing around our galaxy, the immense tidal forces can literally strip gas from them, stretching it into long, streaming arcs that fall toward the disk. Some high-velocity clouds could be the dismembered remains of these galactic companions, their identity lost but their material destined to join our own. The third major theory turns the story inward. This is the galactic fountain model. Remember the violent feedback from supernova and stellar winds. That energy can launch fountains of hot gas high above the galactic plane. This gas travels upward, cools over millions of years, condenses into clouds, and then falls back down under gravity, raining fresh material onto the disk. In this view, high-velocity clouds are not invaders but returning citizens, part of the galaxy's own circulatory system. The truth likely involves all three processes. Some clouds are intergalactic immigrants, some are shredded satellites, and some are recycled galactic material. Telling them apart is a detective's challenge, requiring precise measurements of their chemical composition. Gas that has been cycled through stars will be enriched with heavy elements, while pristine, primordial gas from the intergalactic medium will be almost pure hydrogen and helium. Observations so far show a mix suggesting multiple origins. Their ultimate fate, however, is clear. These clouds are falling into the Milky Way's gravitational well. When they eventually collide with the thicker gas of the galactic disk, the impact will compress them, potentially triggering new waves of star formation. They are a primary source of galactic accretion, the process by which a galaxy gathers fresh fuel from its surroundings to keep making stars over billions of years. Without this inflow, a galaxy would eventually consume all its available gas and starve, its stellar fires flickering out. The silent descent of these high-velocity clouds is therefore a lifeline. They represent the galaxy's connection to the vast reservoirs of the circumgalactic medium, the thin, hot gas that envelops it. By studying these enigmatic travelers, we are watching the Milky Way breathe in, a slow, deep inhalation that will determine its future brightness. What other invisible rivers are flowing into the galaxy, unseen and unheard? The silent rain of high-velocity clouds is a gentle infusion, but the interstellar medium is also pierced by a relentless, invisible radiation. We have already met cosmic rays as mysterious high-speed bullets, but their true role is far more subtle. They are the ghostly chemists of the dark, while starlight, especially harsh ultraviolet, is the great sculptor of the outer cloud layers. It cannot penetrate the dense, dusty hearts of molecular clouds. In those lightless nurseries, cosmic rays become the dominant source of energy. A single high-energy proton can tear through the cloud, colliding with molecules and stripping away electrons, creating reactive ions. This act of ionization is the spark that ignites a hidden chemical furnace. The newly formed ion, now hungry for an electron, will aggressively pull a molecule from the gas or steal an atom from a dust grain, triggering a cascade of reactions. This process can build complexity, transforming simple molecules like molecular hydrogen and carbon monoxide into more elaborate species, including the precursors to organic compounds. The profound puzzle is that we do not know the exact recipe. The cosmic ray flux is not constant. It varies from place to place in the galaxy. influenced by nearby supernova remnants or the shielding of magnetic fields. A cloud bathed in a higher flux of these particles will have a radically different internal chemistry than a shielded cloud just a few light years away. In one, the enhanced ionization might drive the rapid production of complex organic molecules on icy grain mantles. In another, that same intense radiation could be destructive, breaking apart delicate molecular chains as quickly as they form. This invisible variability means that two seemingly identical clouds could be brewing utterly different chemical soups, setting divergent paths for any planetary systems that later coalesce there. This places cosmic rays at the very heart of the probiotic mystery. The chemistry they drive in a dark cloud becomes the inherited chemistry of a protoplanetary disk. If a cloud's cosmic ray environment favored the production of certain amino acids or sugars, those molecules could be baked into comets and asteroids, later delivered to young, rocky worlds. The cosmic ray flux during a solar system's gestation might be a hidden factor in its potential for life. It is a staggering thought that the habitability of a distant exoplanet could be influenced in part by the ancient, unseen particle rain that fell upon its birth cloud millions of years before its star even ignited. We are only beginning to measure these variations and model their chemical consequences, trying to read the invisible writing left by these atomic bullets on the fabric of future worlds. The ghostly chemistry of cosmic rays unfolds within a galaxy threaded by invisible lines of force, a structure we can only see because of a subtle theft of light. Starlight reaching us from distant suns carries a hidden signature, a faint twist in its orientation called polarization. This is not a property of the stars themselves, but a fingerprint left by the journey through the interstellar medium. It is caused by the precise alignment of countless needle-like dust grains, all pointing in the same direction like a cosmic compass. Their orientation is our primary window into the galaxy's magnetic field, but the reason they align at all is a beautiful and intricate puzzle. Why should these microscopic specks, buffeted by random collisions with gas atoms, choose to spin in unison with an invisible force? The answer lies in a delicate balance of torques and forces acting on a grain's rotation. If dust grains were perfect spheres, they would spin randomly, tumbling in every direction. But interstellar dust is not spherical. Observations strongly suggest the grains are elongated, more like microscopic rods or flattened disks. This asymmetry is the key. A non-spherical grain spinning in a magnetic field experiences a subtle braking force if its material is even slightly magnetic. This process, called paramagnetic relaxation, works because the grain's material is not a perfect superconductor. As the grain spins, its imperfect magnetism causes a tiny lag in its internal magnetization compared to the external field. This lag creates a drag, a torque that slowly forces the grain's axis of rotation to align perpendicular to the magnetic field lines. Think of it as the magnetic field gently coaxing a spinning top to stand upright along a specific direction. It is a slow, steady process, but over millions of years in a quiet cloud, it could bring order to chaos. However, many astronomers believe paramagnetic relaxation alone is too weak and too slow, especially in the more turbulent, diffuse regions of the interstellar medium. A competing and perhaps dominant theory involves the power of starlight itself. This is the concept of radiative torques. When a photon of light strikes an irregular dust grain, it does not just get absorbed or scattered evenly. Because the grain is lopsided, the photon imparts a tiny twist, a minuscule rotational kick. The exact effect depends on the grain's shape, composition, and how it is oriented relative to the light source. Over time, as trillions upon trillions of photons strike from all directions, these tiny kicks do not cancel out. Instead, they can drive the grain to spin up to incredible speeds and, crucially, can also force its axis of rotation to align in a specific way relative to both the magnetic field and the direction of the starlight. It is a far more dynamic and powerful process than the slow magnetic drag. The leading models now suggest a complex partnership. Radiative torques from starlight might spin the grains up to high speeds and provide the primary aligning force, while the magnetic field then acts as a guide, defining the specific direction of alignment within the cloud. The grain's rapid rotation causes it to behave like a tiny gyroscope, and the magnetic field provides the stable framework around which that gyroscope processes, locking the alignment into the field's orientation. This interplay is exquisitely sensitive to the grain's properties. A grain made of graphite aligns differently than one made of silicate. A grain coated in a mantle of ice will respond to radiation differently than a bare, rocky core. Even the size is critical, as smaller grains are spun more easily by random collisions with gas atoms, which can fight against the aligning forces. This is not an academic debate about microscopic physics. The correctness of our alignment theory directly impacts how we read the most important maps of our galaxy. When we measure the polarization of starlight, we translate that twist into a map of magnetic field direction. But if we misunderstand the mechanism, we might misread the map. For instance, if radiative torques dominate and align grains relative to both starlight and the magnetic field in a complex way, the polarization pattern we see could be a convolution of both effects, not a pure tracer of the field. Interpreting these maps incorrectly would mean we are drawing the galaxy's magnetic skeleton with a distorted lens. Furthermore, understanding alignment is fundamental to the grain's own survival and dynamics. A rapidly spinning, aligned grain will experience different forces as it moves through the magnetized gas. It will drift differently, it will collide with other grains at different angles, and its charged surface will interact with the plasma in unique ways. The silent, ordered spin of a dust grain is a nexus where the radiation field of stars, the magnetic architecture of the galaxy, and the microphysics of the solid state all converge. By deciphering why these tiny specks choose to point in the same direction, we are learning to read the true handwriting of the forces that sculpt the darkness. The silent spin of dust grains reveals a hidden world of extremes. Beyond the familiar specks that dim starlight lies a shadow population of particles, both unimaginably small and surprisingly large, whose existence reshapes our understanding of the interstellar medium. This is the mystery of the cosmic dust distribution, a puzzle that stretches from the scale of molecules to the scale of viruses. At the smallest end, we find the transiently heated nanoparticles. Imagine a grain so tiny it contains only a few hundred atoms. When this minuscule speck absorbs a single photon of ultraviolet starlight, the event is not a gentle warming. It is a cataclysm. That one photon carries enough energy to blast the entire grain to temperatures of over 1,000 degrees in an instant. For a fleeting moment, that nanoparticle glows like a microscopic star in the infrared before it rapidly radiates all that heat away and plunges back into the frigid darkness of space. These particles are not in equilibrium, they are in a state of constant, violent fluctuation. They dominate the infrared emission we see from many interstellar clouds, creating a warm, diffuse glow that had no clear explanation for years. What are these tiny, volatile specks made of? Are they fragments of larger grains shattered by cosmic collisions, or are they built atom by atom from the gas, condensing like soot in a stellar wind? Their composition is a key piece of the puzzle, as it determines how they absorb light and how hot they get. On the opposite end of the spectrum are the large macromolecular compounds. These are not dust grains in the traditional sense, but sprawling organic molecules. The most famous candidates are the polycyclic aromatic hydrocarbons, or PAH. Picture flat, flaky molecules like tiny hexagons of chicken wire made from carbon and hydrogen atoms. They can contain dozens or even hundreds of atoms, putting them in a strange borderland between a molecule and a solid particle. They are incredibly robust, able to survive the harsh radiation fields that would destroy simpler compounds. When they absorb ultraviolet light, they do not heat up like the nanoparticles. Instead, they vibrate in specific ways and re-emit a distinctive set of infrared bands, a chemical fingerprint we see across the galaxy. Their presence is a direct signal that the interstellar medium is not just mineral, it is profoundly organic. The central question is whether these two extremes, the tiny, heated nanoparticles and the large, flaky pHs, are related. Are they part of a continuous family with pHs representing the very largest of the small grains, or are they entirely separate populations with different origins? Some scientists theorize a life cycle. Large pH molecules might be the building blocks that stick together to form the very smallest graphite grains. Conversely, the shattering of larger silicate or carbon grains in interstellar shocks could produce a cascade of fragments down to the size of pHs and even smaller. This cycle would mean the interstellar medium is constantly processing its solid material, breaking it down and building it up in an endless loop. The behavior of these extreme particles is anything but minor. They dominate the thermal and chemical state of vast regions. Because they are so efficient at absorbing starlight, they become the primary heaters of the interstellar gas in many environments. The photoelectric effect we discussed earlier, where a grain emits an electron after absorbing light, is most efficient for these very small particles. They are the galaxy's primary photoelectric converters, turning starlight into thermal energy for the gas, effectively setting the temperature of entire cloud complexes. Chemically, their surface area is immense. Though each individual particle is tiny, their collective surface area dwarfs that of the larger classical dust grains. This makes them the dominant catalytic surface for chemical reactions in diffuse clouds, where they can facilitate the formation of molecular hydrogen and other simple compounds. They also provide crucial shielding. A cloud filled with a haze of these small particles can block destructive ultraviolet radiation from penetrating deeply, creating safe zones in the interior where more complex, fragile molecules can form and survive. Their population dictates the very habitability of interstellar chemistry. If we misjudge their numbers or their properties, our models of how clouds cool, collapse, and form stars become untethered from reality. The full census of these shadow particles, from the tiniest vibrating speck to the largest organic flake, remains one of the great unsolved inventories of the cosmos. We are still learning what the darkness is made of on the smallest scales, and every new answer reveals how these invisible specks write the rules for everything larger. These shadow particles drift through a galaxy of stark contrasts, where fire meets ice in a silent, slow-motion war. Our final mystery lies not in any single cloud or hot bubble, but in the frontiers between them. The interface between different phases of the interstellar medium is a place of profound transformation. These are not clean, sharp boundaries like the surface of a pond. They are turbulent, fractal mixing layers, seething with activity on scales too small for our telescopes to see directly, yet governing the fate of the entire galactic ecosystem. Picture the edge of a cold, dark molecular cloud, a fortress of dense gas and dust. Just beyond its borders rages the million-degree plasma of the hot ionized medium. Where these two extremes meet, a maelstrom unfolds. The physics here is a contest between three brutal processes. First, there is thermal conduction. Heat, by its very nature, flows from hot to cold. The searing electrons from the hot plasma can stream into the cold cloud, delivering their energy like a microscopic invasion, heating the cloud's outer layers from the outside in. This leads to the second process, cloud evaporation. The heated surface of the cloud doesn't just warm up, it boils away. Atoms are torn from the cloud, stripped off and dragged into the hot flow, enriching the plasma with heavy elements that were once locked in icy darkness. The third force is cloud crushing. The hot plasma isn't static, it often flows as a wind or a shock wave. This dynamic pressure slams into the cloud like an ocean wave hitting a sandcastle. It compresses the cloud, sculpting its surface into intricate shapes, triggering internal instabilities that can cause the cloud to fragment or be stretched into long, filamentary tails. The central mystery is what happens in the chaos of that contact zone. How much mixing actually occurs? Do the evaporated atoms from the cloud blend smoothly into the hot flow, or do they remain in distinct sheared layers? How quickly does a cloud evaporate completely, and how does that rate depend on the magnetic field, which can act as a barrier inhibiting the flow of heat? We must rely on sophisticated computer simulations to model these interfaces, and what they show is both beautiful and complex. The cloud's surface doesn't remain smooth. It becomes rippled and unstable, forming finger-like structures as the hot gas funnels into its crevices. This dramatically increases the surface area, accelerating the evaporation process. It's like watching a cube of ice melt not by slowly shrinking, but by suddenly developing a porous, spongy texture that allows warm water to rush in from all sides. The exchange of mass and energy across these frontiers is the very engine of the interstellar cycle. Without it, the galaxy would stagnate. The cold clouds would remain forever isolated, never contributing their enriched material to the broader medium. The hot gas would slowly cool and fade without a fresh influx of matter. These interfaces are the recycling plants where stellar ashes are gathered and prepared for reuse. They determine how efficiently a supernova's energy is coupled to the surrounding gas, and they regulate the supply of cold, dense fuel available for the next round of star formation. Perhaps the deepest puzzle is understanding how these violent interactions can sometimes be creative. The crushing pressure of a hot wind can compress a cloud to the point of triggering gravitational collapse, seeding new stars even as it erodes the cloud away. It's a race between destruction and creation, the ultimate fate of the interstellar medium, whether it settles into a quiet, diffuse state or condenses into brilliant clusters of stars, is decided in these turbulent, invisible borders. They are the membranes through which the galaxy breathes, the chaotic workshops where the raw stuff of the cosmos is forever being torn down and remade. What we perceive as the serene void is, in truth, a tapestry of endless collision, where every boundary tells the story of a struggle that shapes the light of future suns. This invisible war at the boundaries is the final, ongoing act in a cosmic drama of 25 intertwined mysteries. We have journeyed from the microscopic static cling of a dust grain to the galaxy-wide pulse of stellar feedback, from the scent of rum in the dark to the ghostly rain of high-velocity clouds. Each puzzle reveals a simple, breathtaking truth. The space between the stars is not empty. It is a vibrant, chaotic, and breathtakingly complex ecosystem. It is a chemical factory, a particle accelerator, a magnetic labyrinth, and a cosmic recycler, all woven into one. To understand where we come from, we must solve the riddles of this hidden ocean. The origin of every atom in your body, the formation of our sun and earth, the very distribution of the ingredients for life across the galaxy, all of it was dictated by the forces and mysteries we have just explored. The interstellar medium is the great connector, the stage upon which the story of cosmic evolution is written. Our journey through its secrets is far from over. In the coming years, a new generation of eyes will turn toward the dark. The James Webb Space Telescope will peer into the hearts of molecular clouds with infrared vision, watching ices form and complex molecules assemble. The Square Kilometre Array will map the galaxy's magnetic skeleton and listen for the faint radio whispers of cosmic chemistry with unprecedented sensitivity. These instruments and others will not give us all the answers. Instead, they will refine the questions, revealing deeper layers of complexity in this cosmic ocean. So the next time you look up at the night sky, see more than the pinpricks of light. See the vast, dark canvas between them. See the swirling clouds where stars are born, the invisible magnetic threads that guide them, and the silent, organic chemistry brewing in the depths. That darkness is alive with mystery. Which of these 25 puzzles captures your imagination the most? Is it the missing atoms, the spinning nanoparticles, or the violent frontiers where fire shapes ice? Share your thoughts below, and let's keep wondering at the grand, unsolved puzzle that fills the space between the stars.